Hey everyone, this is Andrew, and here's another formation for you. Instead of going through other stuff, we're going to define fields once and for all. Fields are an n-dimensional structure that observes values. So it's not a function that has input-output. Fields, they're more like computers, or not computers, they're more like programs, and it's not even that too. It's sort of like programs, but it deals with values as our measurement. So measure, which are values. If they're undefined or not, we can come up with conclusions. Specifically in a theoretical format. So if A or if P, Q. We can do equalities or inequalities. So now, what are some values? What are some examples of these values? We have scalar values, which deal with the amount. So we have a line segment, alpha, and we have A and B. We also have points in between. They're all in alpha, and all of these, they apply as scalar values. For direction, let's say we use array epsilon, where we have this. You have one point here, another point here. So this point is A and B. Just a general direction of array epsilon, it's equal to east. So using our Cartesian coordinate system, north, east, south, west. And everything in between, it's just east. Basically, the same goes with points too. So the direction sub A of epsilon is not equal to the direction sub B of epsilon. You could represent it in a different way, but points, they account for tangent lines like a function. Knowing about their speed or just their lines, they account for the direction too, just as long as we have a ray. We'll talk more about that later, but for directional movement, just directional movement, we just need to know what or where an object is moving to. So we have a field, it's moving in a certain direction. So it's not pointing somewhere, it's moving at that area. We can find the rate, or we can make up a rate, and with that rate, we have another value called time. We have a time where it's initial, so t sub 0, well, that's just t sub 0 of, let's do alpha again, t sub 0 of alpha. It's there. And instead of using equals, it just yields something. It results in something, if that makes any sense. So now, we also have rotation around a point. So if we have this, we have a point Q. Yeah, you can just do R, just like R of, let's say R base Q of some sort. Okay, let's use alpha once more. R sub Q of alpha. And, okay, this is a bit weird. We have a rotation value. So instead of using R sub Q of alpha, we need to make sure we have the amount of rotation, whether it's going clockwise or counterclockwise. Yeah? I'll just leave that one for debate, or probably in a different episode. We have lots of other values to account for, and I'm pretty sure there's more on the list. But for now, let's go with rays. Rays are very simple looking field. But I am actually going to redefine array. Just array. And you might as well have seen it in geometry. It's just a line with a starting point extending infinitely in one direction. Okay. Remember when I used to say that it would go anywhere? It's going to be direct no matter what. So it's going to be extending towards infinity. Which is good because I used to do this kind of array where you have another arrow, but okay, no need for that anymore. Instead, we can just have an array looking like this, where we don't know where it's going to go. The same goes with a lot of other structures. And we have fans looking like this. This is a fan. A fan is just a bunch of rays, just all there. They're all touching each other, and we don't have nothing here, just no values. Let's go back to another value, which is pretty important. Values, representations, they're all there. We happen to use set theory, but let's go back to position. Position is another important. So when you're talking about time and directional movement of something, we also need to take into account of position. So we have a point A, and position of 0 of A, it's just right there. We can't really represent it in a coordinate plane because look at it, it's pretty abstract. So let's say this is just for t sub 1 of beta, and then over here is A2. This is just t sub 1. Let's do t sub 0, the initial time, and then t sub, let's call this alpha. T sub alpha. So we know that for t sub alpha, t sub alpha of beta, we know that this yields something where the position, let's just do alpha again, position sub alpha of A is not equal to the position sub 0 of A. It changed over time, just like that. Of course, points can be a direction, or not a direction, but a type of object to use for fields. Again, with the play-place analogy, it's knowing where things are at specific times, and we've already talked about intersections, where we have a point that is on two rays, and we'll get back to rays later in the year. For fields can be curved, of course. Fields can also be n-dimensional, so it can exist in the second dimension. We can have both dimensional, we can have more than one object. So we have lots of rays already, but we can use a plane, or just like that. Technically it's not a plane, it's more like a piece of paper, just a rectangle. We have a ray going over here, and it's touching one point. It's intersecting one point, as of now, like this. That still applies. You can have all of the theories, or all of our conclusions, all kinds of values. If you can move the paper, move the rectangle, maybe rotate it, everything can apply. We can also use cubes or prisms. That can work. We can use different types of planes that some of which might not even apply. So we can just have let's say 2 rays, and then this ray can be set up in a way that it won't even touch this other ray. Like in a way it's going forward. Forward, this is going up. Yeah, we managed to have all these types of conclusions, and that's amazing. So now, where can we go from here? It's a good question. We can have as much fun as we want, but the rest is up to you. So thanks for watching. See you next time.